It is a great pleasure to welcome all the participants to this event. And this is the first RISMIB event which goes virtually live. And I want to thank in particular Professor Italo Capuzzo Dolcetta, who accepted this new challenge of giving the RISM course through this new format. And the spirit of the RISM course is to bring together young researchers and experienced researchers who gave a special contribution to the field. And this is the fourth edition, and the first one was by Umberto Mosco, then Arrigo Cellina, Vieri Benci, and this is for sure the case of Professor Italo Capuzzo Dolcetta, with whom I have the privilege of sharing also a friendship, who has connections with a person who passed away this year, in Nuremberg. I'm sure Italo will join me to dedicate this first event of RISM to his memory. So I give the word to Professor Italo Capuzzo Dolcetta.
Good morning to everybody. Good morning, Daniele, Professor Cassani, for the kind invitation to give this course. As you know, the course was scheduled at the end of February this year, but we had this global accident, and so we are working online, which is not the best solution. Courses are best given in physical, in a room with students attending. And also I am not experienced with this technology, so I hope it will work. And so I prepared the slides, a number of slides, which will soon appear on the screen, hopefully. And the slides are in English, and I realize there are a number of foreign participants, so I think I better speak in English as well. And please ask questions if you feel so. And the idea of this course was to give lectures on the maximum principle for elliptic equations. And the level of generality is not clear, since I have no exact idea of the participants. So I decided to start from a very elementary notions and then go further and further towards recent results, which I obtained in recent years, and which maybe open new direction of interest for participants, at least some participants. And the Detours the title will become clearer in the next lecture, perhaps. So this title is a dedication, which is in Italian. I translate. This lecture dedicated to the memory now of a dear friend, great mathematician Louis Nirenberg. I learned a lot from him, and in mathematics and several things. And I'm pleased to show you the pictures of halva, which is a Middle East cake, which I didn't know until I came to New York, which is not the Middle East, of course, but Nirenberg was pleased to offer me, and I enjoyed very much his friendship and also this little sweet cake. This picture is represents Louis Nirenberg. Of course, this is Louis Nirenberg. This is Umberto Mosco, who was my thesis advisor in Roma almost 49 years ago. This is myself. It was taken, this picture was taken in September 2008, where my friends organized a conference in Roma to celebrate one of my several birthdays. Okay, and this is the index, sort of index of the lectures. There are 10 issues, like 10 lectures, but of course in the presentation will be some intersection overlapping or so. So the first lecture, this one, is about some very elementary issues, I would say. I will tell you about linear, convex, and subharmonic functions in the traditional, classical, smooth sense. Then we will go in a few classical topics on harmonic function, which are, in some sense, at least for what we are concerned in this course, a generalization of linear functions, if you like. Then we will go into the more sophisticated but still classical topic of maximum principle for elliptic partial differential inequalities. And the main result in this direction is perhaps the Alexander-Backel-Mampucci estimate, which is a fundamental tool in all the theory of elliptic equation. And then we'll go to something less classical, but perhaps well known already, is the generalization of subharmonic functions. In the first 4 lectures, harmonic will be essentially, or subharmonic will be C2 function or some degree of regularity. In the 5th lecture, we will introduce the generalized subharmonic function, which are just continuous or semi-continuous. And there are several notions of generalized subharmonics. I will describe briefly the first 2, which are perhaps the initial ones, those coming from potential theory. And then a notion introduced by Calabi many years ago, which is slightly different, but it's also very similar, but not the same, as the most recent, but now it's almost 30 years, that of viscosity, the viscosity notion of harmonic, subharmonic, and so on. Then I will go to nonlinear issues, talking about viscosity solution, a quick compendium of the theory of viscosity solution. And the last lecture, issue number 7, goes in the direction of unbounded domains. In the previous lecture, we'll always talk about function defined on bounded open domain over N. And the weak maximum principle will be discussed in this framework, in this setting. In issue 7, I will touch the problem of unbounded domains, which poses some challenges, in fact. Most of the results which hold in bounded domains are not true in unbounded domains, very simple examples. Number 8, on number 8 we are back on bounded domains, and I will discuss an important issue, which is to find a numerical criterion for the weak maximum principle. This has a long history, essentially is related to the sign of the principal eigenvalues of the operators involved in the equation or the inequality. And there are classical and recent results for this problem, which saying essentially the maximum principle holds if and only if some number, which may be the principal eigenvalue, if any, or some generalized principal eigenvalue is strictly positive. Number 9 is very recent, is in fact a result which I found this in the lockdown period, which is maybe for some purposes it's good to stay at home and think and try to do some mathematics, is the weak maximum principle for system of elliptic equations, for some systems, I should say. And also this, the maximum principle for systems is not given for free. In fact, in most cases, it's not true. But there are some cases in which it holds, and I will present these results, which are very recent. Last topic is a digression into numerics and linear algebra to show that some ideas which I presented before elliptic equation have some implication in terms of numerical analysis of these equations, and also there is a connection with very classical topics in linear algebra. I mentioned before the principal eigenvalue for an operator, and of course the eigenvalue are fundamental tools, objects in linear algebra, and there is a connection between the results in number 8 and classical results in linear algebra, which go back in finite dimensional, so in a finite dimensional setting, which go back to Platon-Frobenius theorem for non-negative matrices. And I hope I will make this program, I will go through this program. In fact, there are quite high number of slides, and perhaps something should be cancelled in the path we will gonna follow. Okay, let's start with section 1 and say something very simple, very, very elementary about this issue. Function attaining the maximum value on the boundary of some set. Which function attain the maximum value on the boundary of any connected bounded set of Rn? This is a function which have this property, max of u over all omega bar is equal to the max of u on the boundary. And this function is said to satisfy the maximum principle. So this is the very basic issue of this course. In dimension n equal 1, so if omega is, say, an interval on the real line, of course, for functions which are monotone, non-decreasing, satisfy the maximum principle. There is a small picture here. If u is monotone of any kind, monotone increasing satisfy the maximum principle. The maximum is attained at the right-hand side of the interval. Functions which are monotone decreasing satisfy the maximum principle because they attain the maximum, of course, in the left-hand side of in the left-hand extreme of the interval. Functions which are convex, minimum principle, of course, we didn't say what it means mean u over omega bar equal mean u on the boundary. And this is very trivial monotonicity property. Still in dimension 1, convex functions satisfy the maximum principle not the minimum principle. And the proof in first course of calculus is a very elementary one. I plugged the picture concerned monotone convex, but if you think a little, this property holds also for monotone, for convex non-monotone like x squared. If you think about x squared, the maximum is attained at the boundary point. And the minimum is attained inside. And so the convex function in dimension 1 satisfies the maximum principle, and concave satisfies the minimum principle. This is very, very elementary remark. If we go to a higher dimension, the situation is of course more complicated, more rich. In dimension greater than 1, the affine function of this form, P scalar dot product with x plus b on any bounded omega, satisfy both the maximum and the minimum principle. And which is the reason? And very simple. If the coefficient of this line is non-zero, the gradient of function u is identical equals to vector p, so u does not have an interior critical point because the gradient never vanishes, and the maximum point, which is attained of course by Weierstrass theorem if omega is bounded, lies necessarily on the boundary of the domain. So, linear affine functions satisfy the maximum principle. And also the minimum principle for exactly the same reasoning. The gradient never vanishes. Of course, if vector p is 0, then u is constant. And all points are maximum and minimum. So, this argument is based on the notion of critical points. Maximum or minimum interior points must be critical, must give a zero value of the gradient. But this is not the true understanding, because of course there are functions which have interior critical points and satisfy the maximum principle. This cannot be affine by the argument before. And a very simple example in any second year of calculus is provided by the function x1 squared minus x2 squared on the ball. The origin is a critical point, the unique critical point, which is neither a maximum nor a minimum, is a saddle in fact, and the maximum is attained, for example, at the boundary point 1, 0. So critical points are related, of course, to maximum and minimum, but the issue of the maximum principle, that is, which function assume maximum value at the boundary, is not completely described by the analysis of critical point. This is a little detour, which justify a bit the title of this course, which is again on linear function, affine function, linear function, and is about the linear programming problem. It's a problem in optimization theory, operational research, is a fundamental tool in applications of optimization. So the problem of linear programming is to maximize a linear function, p c dot scalar product with x, where p is a polyhedron, closed polyhedron, that is a set in Euclidean space, which is defined by affine inequalities, a system of affine inequalities governed by some metric A of appropriate dimension, m cross n according to the situation. So look for X which maximize this Px, where X is constrained to satisfy these inequalities. Of course, a set like this can be empty, can be bounded, can be unbounded, of course. Assume for simplicity for this argument here, which is perhaps two-dimensional, non-empty, and bounded also. Of course, this is a simplification in an assumption which simplify the simple discussion below. So, for what we said before, the maximum of this function is attained at the boundary, because this is a linear affine function, and we assume that this set is closed and bounded, so it's compact, the maximum exists, is attained at the boundary. The boundary is the union of the edges of the polyhedron. So in two dimensions is a polygon, a pentagon, a quadrilateral, anything. And the edges have some vertices, x1, xk, depending on the situation. So the conclusion, by using this fact, is the maximum of our linear function is the maximum of these k numbers. You just have to look. There are two arguments here. The maximum is attained on the edges. The edges are piece of lines, in two-dimensional piece of straight lines. For what we said before, the maximum of a straight line is attained at the boundary. The boundary of these straight lines are what I call the edges. So in two steps, the conclusion is that the maximum of the whole polyhedron is the maximum between the k numbers, which are the values of the linear function, which we want to optimize, evaluated on these finite number of edges. So this is a nice formula because reduce this problem to the comparison between k values, k numbers. And this argument holds in any dimension. And so the linear programming can be reduced in principle, using this argument, to the computation of just a finite number, which may be very large because this number of edges may be very high in n dimension. So it's theoretical, and of course does not solve the problem of determining the coordinates of these points, because you have to solve a very large system of linear equation, which is, anyway, the simplex algorithm, which is perhaps the most famous algorithm to solve the linear programming problem, is based on the maximum principle, because it makes a search, algorithmic search of these edges. And therefore, then, by this theoretical argument, solves the problem. Okay, so this is about linear function, which are, as we have seen in one dimension, convex function have the maximum principle in one dimension. And this goes through to a higher dimension. The notion, this is a citation from Jensen. Often we say Jensen inequality or Jensen in probability theory in convex analysis, but correct spelling pronunciation is Jensen, because he was a Danish mathematician who published one of the first papers on convex function in 1906. And I want to read with you this notion. It seems to me that the notion, I don't know why the citation is in English and the title of the paper is in French. Of course, I didn't check the original paper in Acta Mathematica. Anyway, it seems to me that the notion of convex function is just as fundamental as positive function or increasing function. Positive function is clear, increasing function means positive derivative, and everybody knows that convex function in 1D means, for smooth convex function, means positive second derivative. So the notion of positivity is a crucial notion in analysis at different levels. First order, zero order, positive function. First order, increasing. Second order, convex. If I'm not mistaken in this, and he definitely is not, he was not mistaken, the notion ought to find its place in elementary exposition of the theory of real function, which was not the case, of course, at this age, but now it is. So, going back to our question, which functions satisfy the maximum principle, we made a jump to make a jump now to general and final dimension n, and we look at convex functions. Picture with second lines. I don't, since we are a bit late, I don't make this picture now because I want to go ahead. The picture is the typical one we have seen several times. Convex function whose graph lies below the second line between 2 points for any pair of points. So they are below straight lines or planes which the same endpoints. And the formulation is this: convex function are functions such that for any pair of points in a convex set omega, the difference between ux, uy is bigger or equal than this number. This number is the increment of the function u along the segment connecting x and y, and this holds for any lambda positive in 0, 1. For lambda equals 0 is trivial, lambda equals 1 is trivial, and also in the intermediate point. This is a translation of the picture I described by words. A very elementary fact is quite clear from the definition, is that if u is C1, so as a first order differential, first order gradient at any point, this implies letting lambda to 0, this inequality between the values of ux and uy and the value at these points of this linear function. The linear function, this is p in a generic linear function, and this is the increment of the points. And this implies immediately that if y is interior critical points, this gradient is 0, so this is 0, so means that u of x is bigger than u of y for any x, so interior critical points are minima. This is a key property of convex functions. So this means immediately See, if omega is bounded, then he has a maximum, function u has a maximum on omega bar, and this maximum cannot be in the interior because only critical interior critical points are minima, if any. And so the maximum principle holds. Any maximum point of omega lies on the boundary. Okay? Okay. And there is an obvious duality between concave and concave function. Concave function are just the opposite, the minus a convex function. So, when you go from plus to minus a function, maxima become a minima, and okay. So the minimum principle, for the same reason, holds for concave function. And the linear affine function are both concave and convex. And as we have seen already before, affine functions satisfy both the minimum and the maximum principle. I think this is very simple. And we go a little bit further, especially in view of further developments. As I said before, in one dimension, the convexity of a C2 function is the positivity of its second derivative. If we are in n dimension, there are several second derivatives. So the notion, the order in n dimension is a much more delicate notion than in one dimension. Of course, it's clear to all of you. So if u is convex is a function of n variable, which is convex and C2, then you can look at the analog of the second derivative, which is the Hessian matrix, which I denote by nabla 2 u of x. Is a matrix of is a square matrix, n by n matrix, containing all the second derivatives. All the second derivatives, if u is C2 is symmetric by a famous theorem in second year calculus, the Schwarz theorem is a symmetric matrix. On the diagonal, you have the pure derivative, second derivatives. Off diagonal, the mixed one, but there is a symmetry. The matrix coincides with this transpose. And if u is C2 and convex, we can give a slightly different, quite different proof of the fact that convex functions satisfy the maximum principle. The previous proof was based on the notion of critical point. And we have realized that interior critical points are necessarily minima for convex functions. Okay? Here, we don't look at critical points. We suppose that u is C2. And we use the fact that a convex C2 function has a Hessian matrix which is positive semi-definite. This is a fundamental fact, meaning that if you compute the Hessian matrix of any vector psi in a Rn, then take the inner product with psi itself, this gives you a non-negative number for any psi. Of course, for psi equals 0, it gives 0. And for other psi's, may give you 0 or positive, no negative value of this quadratic form. So if we start from this, and this is pedagogical, to give this different proof is pedagogical for in view of further developments. On this basis, you can produce a different proof of the maximum principle. So you perturb your convex function u by adding this term, which is a positive number epsilon, and this is the square of the norm of x. Norm, Euclidean norm, sum of the squares of the components of x. So u is already convex. This is convex also because the square of the norm is convex, epsilon is positive, but it's in a sense more convex than u. The function u epsilon is more convex than u because you add something which is stronger. Compute the Hessian. The Hessian of u epsilon is trivially the Hessian of u plus the Hessian of this simple function, and the Hessian of square of the norm is the identity matrix. And then there is epsilon and 2 epsilon because you take the derivatives. Okay? And what happens then? This Hessian is strictly positive because this is strictly positive definite. I mean, this property holds true. If you multiply by xi and dot inner product of xi, you do this and you find this. So the original function u was positive semi-definite, weak inequality here, and here you have a strong inequality because instead of 0 you have something which is positive for all xi except xi equals 0. So this function is, the quadratic form is positive definite. Okay, now assume that u epsilon, the perturbed function, attains its maximum at some interior point x bar. Think about this, we are in n dimension. This function is convex, because it's more convex in the sense of u, and attains a maximum at an interior point. Then, again, elementary calculus, you know that the gradient vanishes at that point, but what is more is that the Hessian at this point is negative semi-definite. Concavity at the maximum point, the shape of the function is like this. So the Hessian is concave locally. So the Hessian is negative or semi-definite. Therefore, this is a contradiction because this is less or equal than 0 by elementary calculus. For this calculus, this is strictly positive. So this is a contradiction. And the maximum must be attained at the interior. So this for function u epsilon. So we apply to function u epsilon, the perturbed one, this simple calculus argument to conclude that u epsilon cannot have interior maximum points. Now we have to go back to the original function u. I repeat, this is a pedagogical argument because in several more sophisticated versions will be used later. Therefore, the max of u epsilon on omega bar is the same as the max on the boundary. Then we want to let epsilon go to 0 to recover some information on the original function u. Now we use the boundedness of omega. Means that omega is contained in some large ball. Therefore, the value of u epsilon at any x, which is this by definition, is less than the value of u plus this number, epsilon r squared. Obvious. Therefore, the maximum, the values of this perturbed function, which is less, of course, than its maximum value, and the maximum value, as we have seen, is the maximum, as the same as the maximum on the boundary. And the maximum of the boundary, thanks to this simple inequality, is less than the epsilon r squared plus the maximum of u on the boundary. So let epsilon go to 0, this goes to 0, this goes to 0, meaning that u of x at any x is less than the max of u on the boundary. And this proves that the maximum of u on the whole domain is the same as the maximum of u on the boundary. And this is the proof that, a different proof that convex function satisfy the maximum principle. This is very simple exercise in second year calculus. Okay, I want to conclude with a slide Detours, and then we stop for 10 minutes. So we have used in several points in this discussion, we have used the fact that we are working in the space Rn, meaning that we are working in a space of finite dimension in which bounded closed sets are compact. This is a fundamental fact about finite dimensional spaces. And the theorem, Weierstrass theorem applies, and so on. But this is maybe just a curiosity. The maximum principle it's in some cases true also in infinite dimension for some function. This is just a remark, it's a curiosity. So the remark is like this. Suppose X is a Banach space, say infinite dimensional Banach space. Banach space have a dual space X prime, the space of a continuous linear function on X. It's something like a fine function or linear function on Rn. The norm of the dual space X prime is given over, so the norm of a function, the continuous linear function L, is given by a supremum, is the supremum of the values of L on the unit sphere of the original space X. This is in linear functional analysis, is one of the starting points. This function, L is a linear function, and the norm of L is a convex function. This is easy to check. So this is a convex, one example of a convex function on an infinite dimensional space X prime. So, okay? So it's an example, a specific example of a convex function in infinite dimension. It's quite easy to show using the fact that L is a linear function, that the sup of L over the boundary of the unit ball in the Banach space X is bigger than the sup on the whole ball, the closed ball. This is easy, it depends on linearity. It's essentially the same argument we have evoked in finite dimension when talking about a fine and linear function. So linear functions have this key property, which translates to convex function. This is the maximum principle, of course, for linear function. This property translates to convex function by definition. So the dual norm is an example of a convex function on an infinite dimensional space which satisfies the maximum principle. This is an exercise for if you want to spend a few minutes on this. And the same property, so the maximum principle, holds for any positively homogeneous function of degree alpha bigger than 1. This is a positively homogeneous functional of degree 1. But this degree 1 is not essential. So I propose to stop here for a while and resume in 10 minutes. If you have any question on what we said until now, I think everything was very elementary, but if any, please ask me. No?
Everything was clear. I encourage students to address the questions.
Yes. Maybe now or maybe after the second lecture, if you prefer, as you prefer.
I'm sure, Italo, you would want to be here in my shoes because here is like having students in the classroom, no?
Yes. This is a plus added value to any work. But
I actually have a question.
Some time when you prepare the slides. You spend a lot of time and resources, so it was a pity not to deliver this course.
May I have a question? I want to make a question.
Yes, a simple one, not a professor question.
In the perturbation argument you did, ux plus perturbation in epsilon, there you use the bounded domain, right?
Yes.
But you can also choose the rate of vanishing of epsilon. For example, if epsilon vanishes like 1 over r squared or 1 over r to the power, can you extend this argument also to unbounded domain or not?
Yes, in a sense, yes, but we have for the answer. We have to wait to issue number 8 or 9. Okay. It's a very good question. In fact, we addressed this issue not exactly in this form, but it's if you want to work in an unbounded domain, like a cone, for example. The radius of a cone is something which it's vague now, but if you think about a cone, which is of course an unbounded domain, in the cone live points which are very far, may be very far from each other. Mm-hmm. So there is a number which is not the radius of the sphere, but which is connected to the opening of the cone, which comes into the game when you want to extend the maximum principle to the infinite dimension. At this point, you have to impose some restriction between the rate of increase of epsilon and r, as in your question. It's too early now
we will see.
To say something more specific and more sensitive, more sensible. But this is a good point.
Are there any other questions from students? If not, we make a 10 minutes break.
Can I ask you a question?
Yes, please.
Yeah, just to be sure. When you spoke about the norm of in the dual of Banach space,
Yes.
Yeah, the convex functional on X is the, I mean, L of X.
No. L of X is a linear function. of
Yeah.
X. And the norm of L, the function L in X prime, is convex. The norm, I mean, the function we associate to any L in X prime associate the value double bar L defined.
Okay, so
So it's a real number, the target.
Okay.
And it is convex. It's easy. If you take this is a general fact. If you take a family of linear function in finite dimension, and the linear function and the family is L of X when X varies in the unit ball. For any X, you have no.
Yeah. Okay, understand. Yeah.
If you take the supremum of this becomes a convex function. The envelope of linear function is convex. It's
okay. I understand. But
meta theorem.
In which sense is a convectional function on X? Because for me it seems that
convex function on X prime. This is a mistake in the slide.
Okay, on X prime.
Right.
Okay.
Sorry. The convex function on X prime.
X prime. Okay.
Sorry. It's a mistake. Good.
Okay.
Good. Thank you.
You're welcome.
Make a correction. Sorry.
Thank you to you.
Convex function on X prime.
Okay.
Also, the norm in X is a convex function on X. The norm.
Okay, understand. Okay.
The dual norm is a convex function on the dual space.
In the dual space. Okay. Thank you.
Thank you. So Daniele, we go ahead. Okay.
Very good.
Very good.
Since you are on this remark, is it needed that X is reflexive Banach space or not?
No, I don't think so.
Is independent of that? Yes. Okay.
Yes, this is a remark. In fact, I didn't take this from a book or a paper. It's my remark.
Yeah.
So please take it. It's a little bit with a little bit of doubt, but I think it's not necessary. No.
Okay.
No. Okay. So now we go to a generalization of convex function. A generalization in the direction, having in mind that our main topic is the maximum principle. So we are going to talk about subharmonic functions. And the starting point is, I recall that in dimension 1, smooth C2 convex function are characterized, in fact, by the fact that the second derivative is non-negative at all points. So this positivity property on the second derivative. A natural generalization of this positivity condition in higher dimension is that the Hessian matrix is positive semi-definite. So the inner product between Hessian evaluated, computed on the vector psi, inner product with the same psi is non-negative for any psi. This is positive semi-definiteness. And this condition, in fact, characterizes, as in one dimension, the C2 convex function. And we proved, we have seen, we have given two proofs, in fact, that the C2 convex functions satisfy the maximum principle. That is, they attain maximum value on a bounded set at the boundary of the bounded set itself. So I repeat it very quickly. The analogous of positivity of second derivatives in higher dimension is the non-negativity of the quadratic form defined by the Hessian. And this characterizes C2 convex function. And we have seen, proved, that C2 convex functions satisfy the maximum principle. We gave two different proofs, in fact. This condition implies, in particular, if we take xi as the canonical basis of Rn, the vectors ei, 1, 0, 0, 0, 1, 0, 0, etc. You choose xi in this way, in this formula, sorry. This implies that the diagonal entries of the Hessian are positive or non-negative numbers. You take the inner product, it is immediate, that this gives the diagonal entries, the diagonal of this matrix are formed by non-negative numbers. And the sum of non-negative numbers is non-negative, and the sum of the non-negative, the diagonal of entries of a matrix is what is called the trace of this matrix. Is the sum of the pure second derivatives. And this is also what is called the Laplacian of a function u. The Laplace operator is precisely the trace of the Hessian, or which is the sum of the diagonal entries of the Hessian matrix. So this proves that convex function, this simple observation proves that convex function, that is satisfying what is called SDP, satisfies Laplacian of u, non-negative at all points. Of course, the converse is not true. If the diagonal entries are, if the Laplacian is non-negative, the trace is non-negative, but this does not mean, as simple examples show, that the matrix, the Hessian, is positive semi-definite. Function satisfies what is called SH, subharmonic, are called subharmonic. This is a weaker property than convexity for C2 function. Clear? Convex functions are subharmonic. The converse is, of course, not true, and this is essentially the same example we've seen before. So this function is, in 2 dimension, is 2x1 squared minus x2 squared. And this is a picture. It's neither convex nor concave. It has a saddle point in the origin. And if you compute the trace of the Hessian, that is the Laplacian of this function, it's 2 minus 1. So that the Laplacian is identically equal to 1. This means that u is subharmonic because this is non-negative, but is neither convex nor concave. It's easy to be convinced of this fact. So it is, the Hessian is semi-definite in one direction, is positive semi-definite in one direction psi, and is negative semi-definite in the orthogonal direction. This is the situation. So subharmonic are real special generalization in a sense of convex function. It's not a semi-notion. Why I'm talking about subharmonic? Because this theorem shows that the subharmonic functions in an open bounded set, and if they are smooth in the interior and continuous up to the boundary, still satisfy the maximum principle. Maximum, the whole set, the closed set, is the same as the maximum on the boundary. And this property, maximum principle, I want to point out that implies a weaker information, that if U is negative or zero on the boundary, then its maximum is negative or zero, implies U negative or zero on the whole set. So the sign information on the boundary, negativity, propagates in the interior. Okay, this is a consequence of the maximum principle, and sometimes this is called the weak maximum principle. It's information on the propagation of sign. So this theorem is important, it's a very classical result of this theory, which is a generalization, in fact, of what we have seen for convex function, because subharmonicity is weaker, as we have seen, than convexity, than semi-definite positiveness, which means convexity. Okay? So what really matters for the validity of the weak maximum principle in our setting is not the full property, which is here semi-SDP, but it's just an information of the trace. So what matters is that the sum of the diagonal entries is positive, which does not mean that any diagonal entry is positive, but just that the sum of them, of all of them, is positive. Here, in fact, we have that one diagonal entry of the Hessian is 2, and the other is -1. So the weight of this balances largely the negative weight of this term. So this is subharmonicity. And this is enough for the validity of the maximum principle, this theorem. And the proof of this theorem, I don't want to detail this, but is essentially the same one as we have given for the maximum principle for convex functions. That is, you have a function u which is subharmonic, okay, and you perturb it. You perturb it by adding to u the same term as before, like epsilon norm of x squared. Norm of x squared. As we have seen, if u is subharmonic, then delta u, the Laplacian, is non-negative. If you do the perturbation, you gain a little more. The Laplacian of u epsilon is the same as the Laplacian of u. Then you have a positive, strictly positive term, 2n epsilon, when you compute the Hessian of the function epsilon norm of x squared. And this is what makes the game successful. This becomes strictly positive. Okay? Suppose a global maximum point of u epsilon is an interior point. Again, elementary calculus shows that the Hessian is at this point is a matrix T2 u epsilon, which is negative semi-definite. Remember always that maximum point function looks locally like a concave function, which is this property. So if this is the case, the trace of the Hessian, which is the Laplacian, must be less or equal than 0. Huh? Again, you compute the trace by you select the diagonal entries of this matrix by choosing psi as the coordinate basis, standard coordinate basis. Then the trace is the Laplacian, by definition, is non-positive. And this is a contradiction with this slide, the previous slide, which says the Laplacian of U epsilon is strictly positive. So global maximum points cannot be at interior, so they are at the boundary for U epsilon. And then, again, we want to translate this information from the U epsilon to the original U. And this is done in the same way as we did for convex function, which again use the compactance of omega bar. As you go back to the previous slides and you do the same argument, the domain is containing a large ball and so and so. So that's why I gave that proof for convex function, which is the validity of the maximum principle for convex function is more easily proved by using the critical point notion. But I gave this for pedagogical reason because the same proof goes for the more general case of supermonic. And this is what I'm saying. So I ask you to complete the proof using the limit argument, letting epsilon go to 0 even in this case. So the key point is that perturbations are important because this notion, convexity or subharmonicity, involve just a weak inequality, Laplacian greater or equal than 0, and to conclude by contradiction, you need to have a strictly positive sign, and this is achieved by the suitable perturbation of the subharmonic function by epsilon norm square or anything which has a strictly positive Laplacian. So in a sense, those U epsilon are strictly subharmonic, while U is just subharmonic. Okay? This is side information. This is the basic theorem for basic form of the maximum principle for subharmonic function. That is, function whose Laplacian is non-negative in a domain, in a compact domain. Let's see a special case of function, which are quadratic polynomials. Quadratic polynomials are fundamental object in several points of the theory of elliptic equation, both for linear elliptic equation, both for fully nonlinear elliptic equation. We will see several issues of this statement. So it's important to have a look at specific function like quadratic polynomials. Quadratic polynomials are functions which are of the form of a quadratic form, qxx, q is a symmetric n by n matrix. For example, the Hessian of some function, plus a linear term, p dot x, plus a constant, a number c. If you compute these are C2 function, of course. If you compute the Hessian of this function u, Since this is quadratic, if you compute second order derivatives, there is no surprise that the Hessian is the constant matrix Q. If you differentiate twice a quadratic, then you have it one after in front. The Hessian is exactly the Q matrix, the constant matrix Q, and the lower order terms disappear by second order differentiation. Suppose in particular that Q is diagonal. One special important case, you know from linear algebra that you can reduce to diagonal form in some situation. So Q is diagonal, which means that Q is the diagonal matrix whose diagonal terms are the eigenvalues of Q. This is, if you are not familiar with this, go back to linear algebra text. And that's, or if you prefer, assume that Q is the diagonal matrix whose diagonal elements are its eigenvalues, which are real numbers because Q is symmetric. Okay. So question, when a quadratic polynomial is subharmonic? Well, the answer is simple. Since the Hessian is Q, the trace of Q is the sum of all eigenvalues, which I write as the sum, which I decompose as the sum of the positive eigenvalues and the negative eigenvalues. So quadratic polynomial is subharmonic if this number is non-negative, which means essentially that a quadratic polynomial may have both positive and negative eigenvalues. Remember, convex functions have just positive eigenvalues, greater or equal than 0. Subharmonic may have positive and negative, but the weight of positive eigenvalues is more important than the weight of the negative eigenvalues. This is the meaning of this inequality. So it's very clear, quadratic polynomials are subharmonic if and only if. Now, if U is quadratic, if the quadratic polynomial is subharmonic, then this holds. And we will see next that also the reverse implication is true. So, if a quadratic polynomial has this property, trace of Q non-negative, then the quadratic is subharmonic. I defined the subharmonic function by the inequality Laplacian U greater or equal than 0. And here is a big jump, a little jump, which I misses in the slides. Superharmonic functions are a function for which the Laplacian is less or equal than 0, and harmonic functions are functions which are both sub and superharmonic, meaning Laplacian identical equal to 0. Okay? Like convex, concave, both convex and concave means affine, both sub and superharmonic means harmonic. Okay? So, for harmonic, this quantity is 0, which means there is a perfect compensation between positive and negative eigenvalues in the case of quadratic polynomials. Okay? And this is what happens for quadratic. Okay, well, this is nothing. I said before already that the quadratic polynomial is convex if Q is positive semi-definite. meaning the total eigenvalues are non-negative, and the Laplacian is supermonic. So any convex quadratic polynomial is supermonic. So convex quadratic polynomial is a sort of extreme case of supermonic quadratic polynomial. So superharmonics, I already said something, are functions, smooth function satisfying the opposite inequality, Laplacian negative. And for what we have said before, this means that just the opposite of V is supermonic, and the opposite of a function as the Laplacian of U is the minus Laplacian of V, so this is clear. And maxima becomes minima for when you change sign from plus to minus. So superharmonics satisfy the minimum principle. That's clear. Harmonic, therefore, and this is a theorem, it's a consequence of the theorem on superharmonic. There is an analogous dual theorem for superharmonic, so there is a theorem for harmonic functions. So harmonic functions satisfy both maximum and minimum principle, meaning both max and min are attained on the boundary. So the values in the interior are controlled by the values of U at the boundary. Okay? Okay, I think this is quite clear. We go on further. But this is a simple example of harmonic functions. I suggest you to compute the Hessians and the Laplacian. In this case, is just to make some exercise. This is one of the fundamental harmonic functions in potential theory. And this is a simple, different kind of example. In this case, it's a product of a function of x1, sorry. This is a mistake, I should correct it. This is exponential x1, not a sub 1x. Exponential x1 times sinus x2. This one is also important. This is important in 2 dimensions. These are several examples of harmonic functions which are not convex, in fact. So this is let's go back to the maximum principle for harmonic. This is called the Poisson equation. Find the function U such that the Laplacian equal to 0 in some open set. As we have seen, both minimum and maximum are attained on the boundary. So it's a natural problem associated to the Poisson equation is the Dirichlet problem. The Dirichlet problem means to solve an equation Laplacian U equals something by assigning a further condition, a constraint imposing the values of this function at the boundary. And this is an important example of Dirichlet problem. Consider this Dirichlet problem. Laplacian of U equals -1 in a ball of radius r in dimension n. And you prescribe the Dirichlet boundary condition that U must be 0 on the boundary. So you're looking for a function delta U. U was Laplacian is negative. Is negative, meaning superharmonic, real in particular. but not any superharmonic. A superharmonic whose Laplacian is exactly equals to -1 at any point. It's very easy to check that this function, there are of course several functions whose Laplacian equals to -1. You can imagine several functions doing this. For example, several quadratic polynomials. If you take a quadratic polynomial, u, whose Laplacian equals -1, is easy. Take your quadratic polynomial, choose the diagonal in such a way that the sum of the diagonal elements is -1. Okay, let us go back here. This one, in this example, the Laplacian was identically equal to 1. So change the sign to this function u, and you have a quadratic polynomial whose Laplacian equals -1. Yeah? Then you perturb this with any linear zero-order term, the Laplacian remains the same. So you have plenty of functions which satisfy, plenty of functions which satisfy delta u equals -1. For example, a lot of quadratic polynomials. If you impose u equal to 0, of course, at the boundary, of course, not all quadratic polynomials satisfying this delta u equal -1 will satisfy the boundary condition. But this one does. You see, this is a quadratic polynomial, a concave quadratic polynomial, in fact, because there's -x squared here. And if you compute the second derivatives, you check that this is the solution of the Dirichlet problem, delta u equals -1, u equals 0 at the boundary. Is it the only solution? Well, this is a separate question, but in fact it is the unique solution. But I don't care about this. For this example, it's easy to check that the minimum on the boundary, it's equal to the minimum on the whole set, which is what you expect since this is superharmonic, so satisfies the minimum principle. This function on the boundary is equal to 0, and this is the minimum. 0 is the minimum over all the ball, because inside the ball, x squared is strictly less than r squared. So this number is always positive and becomes 0 only when x is norm x equal r. Okay? So it's not a surprise because we know already that this is a superharmonic. I present this example because, well, this is interesting. I don't know if any one of you has some familiarity with the stochastic process or... Anyway, this function u has a probabilistic interpretation. If you consider what is called the Brownian motion, I don't want to go further on this. The Brownian motion in omega, which starts at time 0, is a process, a stochastic process, a curve, which starts at 0, at time 0 at the point x, and was differential, time differential, whatever it means. I cannot go into details here, is identical equal to 1. So the velocity is constantly equal to 1, moves from x and travels in the domain with velocity 1, whatever this means. Then you can imagine, and I'll give you, tomorrow I produce some picture of this. There is a curve, which is called the Brownian motion, and you can ask yourself, which is the first time in which this curve goes out from the ball. Now I am connected with the charger, so I cannot connect at the same time the iPad to draw a figure. I'll give you tomorrow. And so this curve at some time maybe exits the ball, touches the boundary if you prefer, exits the interior of the ball. Okay? And there is this first exit time depends on the starting position. If the starting position X is on the boundary, the first exit time from the interior is 0. So the first exit time is 0. And this function, if X is on the boundary, is exactly 0. Okay? And what can be proved is that this function gives for any x a number, a positive number, u of x, which is precisely the first exit time of the Brownian motion from the boundary, from the ball. For example, in the book, PD book, equazioni alle derivate parziali, for example, by Sandro Salsa, this is explained in a full way. Okay? And this is a typical fact of stochastic process, the basic stochastic process, the process whose differential in time is identically 1. Now, considering the basic deterministic motion, not the stochastic motion, a differential equation, if you like, starting at x, at time 0, whose derivative in time, the velocity, is identically equal to 1. So this is a very familiar object. What is the solution? If you want a curve starting at x, whose velocity is constant, the curve, so the solution curve is a line, okay? Is a line with constant slope 1, okay? And if you look at this, and this is a computation you can make even if you don't know anything about stochastic and Brownian motion, draw a ball, fix a point x inside, and draw the line exiting at x, starting at x with velocity 1. Of course, there are two lines. I'll give you a picture tomorrow. And the first exit time, so the first time in which this straight line touches the boundary, you can compute it because velocity 1, and it's easy to compute, is precisely the distance from the boundary of the starting point. So absolute value of x minus r is a different function. This depends on the, maybe it's the contrary, r minus absolute value of x is a positive number, so sorry. I have to check this, to correct this. Is r minus absolute value of x. So it's different. The stochastic process depends quadratically on the distance of the norm x, and the exit time for the deterministic process depends linearly, or degree 1, norm of x. And this function is a solution of a PDE, which is, again, there is a mistake here, sorry, which is called the aconal PD, is absolute value of u, of gradient u, at any point x, the next u should not be there, equal to 1. So the equation is absolute value gradient ux equal to 1 at any point of the ball, and u equal to 0 at the boundary. So it's again a Dirichlet problem. And which are the difference between this Dirichlet problem and the previous one? An obvious one is that the first one involves second-order derivatives, Laplace operator. This involves first-order derivatives, just the gradient. Second major difference, this equation is a linear equation. The Laplace is a linear operator. The Laplacian of a linear combination of functions is the linear combination of the Laplacians. This equation, the aconal one, is nonlinear because the absolute value, the gradient is, the absolute value of the gradient is not a linear function of u, because there is the norm of the gradient. The norm of anything is convex, is not linear. Okay? So this is important for several facts. Okay, maybe one more slide. Just to, I think this is, there is no time to touch fully the next topics, but just to introduce. We have been talking a bit about the Dirichlet problem. So Laplace with some function equal a given data, maybe 0, and the boundary condition. There is a theory, old theory, due to Perron. Perron is a mathematician active for a long time in the last years, in the years of 19th century, in the early years of 19th century, so 1970, say, to 1807 to 1910. It's one of my mathematical idols, and I say why. Because Perron published, I don't remember exactly, but maybe 30 papers, scientific papers, after the age of 80 years old. So it's extremely active mathematician even in his old age, and a very important one for several reasons. So tomorrow we start with this, which is called the Perron method for solving the Dirichlet problem, which based essentially on this, and I leave you with this. You want to solve the problem delta V equals 0 in omega, and you want that V coincides, to find a solution which coincides point-wise with some function g given on the boundary, which can be anything in principle. And the idea of Perron is that if you look to all functions which are subharmonic in omega, here you want to find V which is harmonic. The idea of Perron is look at functions which are just subharmonic, so less stringent condition. Of course, there are much more subharmonic functions in a set than harmonic. But coinciding with a given function g on the boundary. So this is a large family of functions which share the property that all of them are subharmonic, and all of them satisfy exactly the same boundary condition. Even in one dimension, you can imagine all convex functions, say, in one dimension, which given value at the end point of an interval. And take the supremum of all of this. So for any x, you choose, you look at u of x, where u is subharmonic, then you look at all subharmonics, so you take the supremum of the number u of x when u varies in the set of subharmonic with fixed boundary data. And this gives you some function v. Okay? This is a definition. And the idea of Perron method is that, of course, this function v satisfies the boundary condition because all function u you are considering satisfy u equals g on the boundary. What is not at all obvious is that this function v satisfies exactly delta v equal to 0, that is harmonic. And this is the Perron method, and the proof is not at all trivial. The proof is not at all trivial because, just for this, and I leave you with this thing to think about. This function is subharmonic. So suppose they are C2. All of them are C2. When you compute the supremum of two smooth functions, in principle, you lose regularity. Okay? Just take two lines, two straight lines. If they have an intersection, these two straight lines, the max, the function which is the supremum of these two, has a corner in the intersection point. So the two lines are C infinity. The max between the two is just continuous. Even the derivatives don't match one side to side. So the key point is to prove that this function is C2. And this is difficult, and it's outside the topic of my course here. And if anyone is interested, the proof is in the book by Gilbert and Trudinger, for example. Why I mentioned this? Because these Perron methods produced, in fact, a continuous function at least, and this continuous function v, this is not quite easy, but it's possible to prove it without much difficulty, is a generalized solution in the viscosity sense, we will see later, of the Laplace equation, and also of a more complicated linear and nonlinear equation. So I think we have to stop here. I have as homework to check, to make correction on the slides, and to prepare a few drawings on the last things we said today. Unfortunately, I cannot do this now because the charger, I have the charger on the computer, and I cannot connect at the same time the iPad and draw a picture. So this will be my job in the afternoon, and tomorrow we go back 5 minutes and start again with the Perron method later.